Actually, we are moving slightly a bit slow, because actually we are already on the day when we shall have to speak start to speak about the critical convection, but we didn't even understand on all the basic things. I tried to deliver these basic things to you in every detail. Maybe I'm wrong in this way, because only 2 days of the course remains, less than 2 days, 1 day and 2/3. So actually, in terms of the lecture hours, so actually maybe I'm just suggesting that I will very briefly introduce you the topic, which are sort of the general topic, and then we proceed to the case maybe on the next lecture, or maybe in tomorrow, but perhaps I hope now on the next lecture today. We proceed to the critical convection itself in a asymptotical point of view in this wonderful solution. We just, of course, it's impossible uh, to deliver to you every detail of all this stuff, because it's vast. So we need to. Let's first stand for the next lecture, which is about kinetic and total energies. And this equation, which is shown here, could be obtained from the Navier-Stokes equation if we just multiply the Navier-Stokes equation by the velocity. So this equation, which is on the display, could be obtained if we just multiply by velocity vector. This is a scalar product. We take the scalar product of the velocity vector on the Navier-Stokes equation, or more precise, or other words to say, momentum equation. And you see that here, on this notation, you see the first things which is appear here is the derivatives of the v square divided by 2. This term is appear from the this scalar product, which we multiply on the dv by dt, partial derivatives of v over t. And so when we scalarly multiply it, we get this obvious result that we have taken into account as well that this adiabatic condition rho a times v vector is divergence free. So we get such a simple stuff. One could ask, where is the v grad v term? It's actually disappeared. It's the advantage of this representation when you multiply by the vector velocity in scalar way. So this complicated nonlinearity is completely absent. And the nonlinearity becomes, because maybe you remember that actually this v grad v is better represented via the v times v times in vector sense on the rotor v, and here if we multiply by velocity, then this term is cancelled out. Another good news that the Coriolis force is also cancelled out from this relation. You see, there is no Coriolis force. And here, this is direct consequences that we multiply the vector of velocity on the scalarly, we multiply on the vector product of the in the direction of the unit vector in the direction of the axis of rotation and velocity itself. So we have again 0 when we multiply scalarly all this stuff. So we give rid from the most difficult terms. And so then the energy balance, kinetic energy balance, of course, this kinetic energy balance is reading quite simply. You see that it's include diffusional term in such a way, and this is only nonlinear term which appear here, and it's quite more easy to treat it. And there is a buoyancy Coriolis term which is here, and there is some remains which we can put in the divergent form. And they are actually on one boundary, working on one boundary, and another on another boundary. if we want to consider the integral of all this energy, the things which I showed previously was only for the case when we have integral, when we have local balance of the energy contribution. But if we integrate, we will get further simplification. We obtain that the total kinematic, sorry, where is the mouse? We will see that this total kinematic energy, this one, in terms of the impulse and everything. So this total kinematic energy has following contribution. First, usually positive contribution is coming from the buoyancy force. It's, you see it is here. And actually all the convection is related on this buoyancy force, where A is the buoyancy acceleration. In our previous formula, which we showed to you, we see that this buoyancy acceleration is due to the variation of the entropy over the adiabatic state and over hydrostatic state. And so it's this buoyancy acceleration is working that it's directly proportional to this component of the entropy. And here there is a contribution from the different terms of the viscosity, and they are also quite simple. And also there are some contribution directly on the boundary, because we have this simple explanation that we have evolution of the kinetic energy due to the, first of all, due to the Archimedean buoyancy term. Then there is negatively defined viscosity of one type and another type. All this viscosity are working on the removing the kinematic energy. So kinematic energy eventually disappear on viscosity if there is no support from the buoyancy term of this term, which is shown here. And also there is some effect on the boundaries. So here on the boundaries, is this on one boundary it works like that. Of course, this effect comes from the viscosity again. And if this boundary rotate, even if this boundary not rotate, this effect occur because it actually depends on the rotor of wave. So, so maybe, so in any case, we should take into consideration. But maybe only in one simple case, when the system is co-rotate, then we have the boundary condition about V. Then in this case, we have the no effect of this force. But it is sort of not good case, because actually all this boundary, if this rotate in our coordinate system, then usually this is not. This is have some differential rotation, and this is the nature. But nevertheless, all this term, viscosity term, especially this one on the boundary, could be neglected, and the major balance, again, just to state you to understand how it works, and the major balance is between the Archimedean buoyancy force and the viscosity. So the next, let's take, so here it's written how this viscosity works, and the normalized heat flux from the viscosity can be represented like that. It's exactly taken from here. So actually it works like that. And also we can take into the consideration not only kinetic energy, but internal energy as well, which is denoted here by epsilon. And here there is we have again the similar balance. And in this case, we should include in the balance the radioactivity heat source, which is usually, for example, in the Earth planet, it could be quite valuable. And this balance in the differential form look like that. And if we proceed further, we can replace the terms from here by the entropy terms, including this entropy terms, which is responsible for the cooling down of the planet. we consists the plant we are discussing. So, oh, sorry. This is the end actually about the kinetic energy. Okay, kinetic and total energy. Is there any question? I'm just trying to to make it more faster without writing on the board. But later, when I will proceed to the crucial to the excitation of the velocity field and convection, then of course I will be in more detail, because the critical convection is one of the most important subjects which we should describe in some detail. But maybe there is some question about kinetic and total energy and other energy. If there is no question, let's proceed to another topic. Okay, we remove that. And then we proceed. We proceed to the chapter which named cooled temperature and pressure be basic thermodynamic variables. And okay, again in short terms, we considering the temperature T and pressure P in the main thermodynamic variable in the equation of nearly adiabatic state, which could be referenced as 4.1. Instead of superadiabatic entropy, we should use the superadiabatic temperature. As a result, instead of 4.1, we obtain. So the result, if you use superadiabatic temperature, this one, and superadiabatic pressure, so instead of the representation via the pressure and entropy, we have representation via the pressure and temperature. And proceed further, of course, we have the variation of the pressure against the adiabatic entropy, the same for the gravity potential, and I just told you this is a variation in the temperature. And then in this case, entropy is not main plane term, and we should separate it out and to represent via this pressure and this super adiabatic temperature. So let's consider how this works in more detail. First of all, we could consider the hydrostatic equilibrium, like it's written here. Then we expand into thermodynamic variables, which are now we're trying to prove that we could use the equation with the temperature and pressure as basic thermodynamic variables. And eventually we have this representation via the modified pressure, which in fact not pressure, but the pressure divided by the density, and there is the inclusion of the superadiabatic gravitational potential, and so on. Also, there is a pressure here. So, of course, we put this everything to the Navier-Stokes equation, and Navier-Stokes equation changed not so much. It's also very similar to the equation we have. And also there is this form of the gravitational potential. And then we should jump to the equation for the the problem is that we first of all, if we suppose that the pressure and temperature is the basic thermodynamic variable, then in the equation for the entropy, we have them both here. You see that the instead of the simple equation for the entropy, where actually the substantial derivatives act only on the entropy, here we should have the equation where the substantial derivatives act to the pressure and the superadiabatic temperature. So there is in the substantial entropy, in the substantial derivatives, which is actually constitute of the derivatives of the d by dt, partial derivatives in time, and it's also include, of course, v grad v term, and this complicated stuff should work not only on one variable but on two. And eventually we have, instead of the simple equation of the entropy, we should, if we separate this two value of entropy of the pressure and the temperature, if we separate these two value on two independent equations, so we have addition. We have extra addition if we, before that, we use only one equation for the entropy. In this case, when we name the pressure and temperature as the basic thermodynamic variable, we, instead of the one equation, actually for the energy, or more precisely for the entropy, we have to use two equations. One for the superadiabatic temperature and one for superadiabatic pressure. So the order of the equation rise very sufficiently. If it was the equation of the second order, so now it becomes equation of the fourth order. And everything is in partial derivatives. Of course, it's much more difficult to solve this problem either numerically or either asymptotically or in any case. So maybe this is, in very short terms, is the proof that we cannot use temperature and pressure as basic thermodynamic variables. And why this question occurs and why this question arises? Because the majority of the work, which is devoted to the planetary dynamics and especially to the some planets where of course the major amount of all the work which are very known in the world, that they almost all of them are having deal with pressure and temperature. They are not preferred to handle with the entropy. But then they use in fact they use the deviation of the temperature, but they are not completely true. They are not completely doing right things, just because they are taking into consideration only one equation, this equation of the temperature. They are not taking into consideration equations for the pressure, which should be appear in this case. And we could give rid of the equation of the pressure in this case, which is written perhaps here. Oh, no, we wrote it in our previous work. Something based on this presentation. And actually, in terms of the pressure and temperature, we have almost equal contribution from the pressure and from the temperature to the entropy. But in terms of the entropy and pressure, we could neglect the pressure contribution. And it we simplify the system very sufficiently, and namely this system is working. And why some people who are doing this stuff still have some success? Just because the entropy equation is quite similar to the thermal equation. But they didn't recognize that they in fact work in the entropy field, not in temperature field. So this is just to show, and also of course we can take into consideration the boundary condition here. But the main thing of all this stuff is that if we want to use the pressure and temperature as the basic thermodynamic variables, we finished up, instead of the second order partial differential equation for the energy, which is in fact entropy equation, we should solve an extra equation. And this it's also pays the problem that because not only this extra expression, you see that this pressure is entered here, and it also involves the gravitational potential. So our problem rises tremendously, if we use the pressure and temperature as the basic thermodynamic variable. So this is sort of all the people to understand how they are working and work in the entropy field if they want to get the right result, and most important with not so much effort as it's required. Okay, so I finished actually very briefly this next paragraph, next chapter, even next chapter, or maybe more precisely to say paragraph, because chapter is more. And so if maybe there is some question about this chapter. Small c square, which in square? This is the speed of sound. Speed of sound, yeah. Okay. And maybe more questions? Okay. Okay, please. Sorry?
This means pressure and temperature can be used as thermodynamic variables.
Sorry?
Pressure and temperature can be used as thermodynamic variables.
In equilibrium?
No, pressure separately or temperature separately as thermodynamic variables can be used.
I don't understand. Sorry.
So basically, I'm asking the topic only that temperature and pressure can be used as variables of thermodynamics.
No. The main conclusion of all this topic that it's better not to use pressure and temperature as the basic thermodynamic variables, because it leads to a lot of difficulties. And in fact, it's much more better to use the entropy and pressure. And this way, when you use an entropy and pressure, all the most important terms of this equation, especially first of all the buoyancy term, then we can neglect the pressure contribution. And if we neglect the pressure contribution, the system is dramatically simplified, and actually it's working much more better in numerical sense, asymptotic sense, in any sense. So this is just a proof that it's wrong way to use the pressure. Yeah, exactly. So okay, so did we finish with that stuff? Okay, if we finish with that, let's stop for the moment. Let's see where we are. So we actually very briefly proceed on 2 paragraphs. And the next paragraph which we have, this Maria give you tasks, so maybe we will not discuss them here. Maria, you actually in our list of the lecture, there is the exercises for the chapter 4 here. And did you finish this already? We discussed it there. Okay, so I proceed further. I will proceed further. Oh, okay, bingo. We on the critical convection now. This is chapter 5. Okay, let's see. Where is it? Okay, we are here. Okay, let's proceed further. I'm missing time a little bit. How many time we spent already? 30 minutes. Something like 30 minutes, yeah? Okay. Okay, so just in 30 minutes we pass it two chapters. So now proceed to the critical convection. Okay. This is the actually section chapter 5. Oh, no, it's writing badly. Okay, we proceed to chapter 5. Its name critical convection. Okay, maybe it's rather important stuff which we now in. And this section 5 is to determine the condition for marginal stability of convection in the liquid core of the Earth type terrestrial planets or moon. These objects are all in the state of rapid rotation, for which the viscous force, as measured by Ekman number E, is many order of magnitude smaller than Coriolis force. Actually, we already stressed on this point that the Ekman number is actually acting like the effective viscosity, sorry. So this is viscosity is 10 to minus 15 for molecular value, and for turbulent value it's roughly 10 to minus 8. So anyhow, it's quite small, and it is many order of magnitude smaller than Coriolis force. Since realistic Ekman number are extremely small, we use asymptotic method based on small Ekman number. In this way, we find new results using the standard local asymptotic method introduced by Roberts in 1963 and Busse 1970. So founder of all this asymptotic critical convection approach was first Roberts, in 1968, and the second is Busse. And Busse in 1970. It's possible to know that later, after the work of the first work of the Roberts on this subject, Busse makes his work slightly, but independently. He made his work independently, slightly from another point of view, stating the same estimations and solving the similar problem. But then later, Busse becomes much more active than Roberts, and he produced a lot of stuff about this convection. And Roberts more famous that later he joined the dynamo problem and successfully resolved in some aspect. And more recently, the method has been refined by Jones et al. And it was some sufficient problem in this first introduction, but then it was refined in some sense by Jones Soward. This Soward, also very important person. I knew him personally. We made some work together, and it was Musa. And it all happens in 2000, where very sufficient correction. Actually, this Roberts and Busse found local solution, but this person managed to find the global solution. So they were using their global WKBG method. Actually, everywhere we use WKBG method. Okay, let's text like that. WKBG KBG method. Maybe you know this notation, but this was local. And of course, with not so accurate. And global was introduced later by those persons, first of all, and it was dramatically better accuracy, very high accuracy. So at the finite Ekman number, all this is based on turbulent transport coefficient, and we calculate the critical parameter of the marginal stability of the convection. Here I just describe the essence of this chapter. And then let's start this chapter from the linear asymptotic system. And the original system of convective equation includes the continuity equation, which you already saw in many occasions, the equation on heat transfer or entropy equation, the Navier-Stokes equations of momentum equation, the equation for the gravity potential, and the equation of states. Well, I will not repeat them here because we already saw them a lot. I just remind you that perhaps the first defined all this set of the equation was Greenspan in 1968, then Landau-Lifshitz in 1988, then Roberts and Braginsky together in 1995. And to obtain the unique solution, the convective system must be solved subject to the corresponding boundary and other necessary conditions. And the using classical Boussinesq approach, actually all these persons were using classical Boussinesq approach, and this, as already told you, Boussinesq was found this approach in 1871. Then before him was Oberbeck, and also Boussinesq make 1903 the work. But here there is some important correction that Boussinesq actually everybody regards that he create his work in 1903, but there is one work in 1871 which Boussinesq did. But it's maybe not precisely the Boussinesq about Boussinesq convection, but nevertheless it give a priority on the Oberbeck, and so it could be fixed and known. And which is probably the simplest and most widely used the initial system can be, and it can be significantly simplified. Actually, the first assumption generally employed in the classic Boussinesq approximation is that of very small relative density variation. And it allows one to use the simplified continuity equation. The simplified continuity equation we use, first of all, that instead of all the substantial derivatives we suppose to put the zero, totally neglecting of the sound effect and sound wave. And it's just simply divergence of V equal naught. And this constitutes the first equation in this chapter. This is, of course, a very simple condition, but nevertheless it's allowed to reach some results. And the second Boussinesq assumption can be expressed in the form of the requirement that the heat of energy variations are mainly due to the temperature variation. As already in my previous talk, I just told you that it's maybe not right way, but in the case when we have could suppose that the divergence is actually not, of course there is some deviation from the divergence just to have variation in the density for convection to rise and to work on. And so this is, but this taken into consideration in Boussinesq approximation only when on this Busse term. So here there is some simplification, but nevertheless it's work. So this means that the heat transfer is described by the well-known Fourier-Thermal equation of heat conduction, which provides the second equation of the Busse system. The first equation is the divergence-free equation. Then the second is the equation for the temperature. Here there is known constant. There is substantial derivative of the temperature over dt. And also there is Laplacian term, which effectively applies the divergence of the following gradient. Kinematic diffusivity K, then grad T. All of this is actually diffusivity contribution. This is Euler type substantial derivatives contribution, and also quite possible that there is an internal heat sources, and they can be written in such a form. And just let me stress that it's not heat flux directly, but heat flux per meter square per area. Perhaps the most okay, started. Okay. Hello, good morning to everybody. I'm glad to proceed. So on our previous lecture, we derived the sort of semi-final system. While I'm naming it semi-final because it's just for some very general form. But to solve some particular problem, we should specify somehow some things which is we will specify here. We could actually specify concrete hydrodynamic instability which work with the convection, because we in our previous formulation, when we formulate the full system, we didn't specify what is the concrete form of all the terms which are responsible for setting on the convection and developing it. So actually the source of the convection, precise source of the convection in precise form was not determined yet. So let's now just finish this work by definition of this model. And so we proceed to the next chapter, which name is 4.3. Convective instability. Stability. I will abbreviate a little bit. And the final system. And the final system. So we now will derive the final system, because it's actually natural to define the convective instability from the stationarity V equals 0 solutions. Actually, you know that when V equals 0, actually the very essence of all this stuff is that we are looking for the solution on the condition that V is 0. It's easy to see that this solution under this condition is not 0. It's some hydrostatic equilibrium. And namely this hydrostatic equilibrium, it's allow us to drive the convection. So actually we take the initial system. I just remind you this initial system, it consists from 4,4A. So we apply this condition to the initial system, which consists from 4,4,8, 4.7, all possibilities, then 4.6 A and D, A to D, and also it consists 4.3 B. So we apply this condition, just this condition, and we look for the solution which further will be indicated by the zero index. So without loss of generality, initial accuracy, see the previous section, and taking into account the limitation of our knowledge about the deep interiors of planets and moons, we will agree to consider the adiabatic density, temperature, and volumetric density to be constant. So we just first additional simplification, when we put first, of course, we put the V equal naught. Then we suppose that the volumetric heat density and temperature, adiabatic temperature, and this heat flow are all constant, just for simplicity. R, T, Q. We just name it without any notation, but we should understand that this is the adiabatic value. And this is actually constant everywhere, but not everywhere, but everywhere except for those places in all this equation, except for those places in this equation where significant derivatives are taken from them. So actually we combine this value from some constant value and with some additional derivatives, which we will estimate these derivatives and gravitational acceleration, determining them in the following way, which is in good agreement with all available studies of planets and satellites. So we just suppose that there is some initial constant, and on top of that there is some variable. So we just suppose that, like it's written here, that direct variable in R, because here when we consider this solution with V equal naught, it's spherically symmetric solution. So this spherically symmetric solution has a property that its first derivatives of the adiabatic density divided by dr is equal specially introduced value rho prime, that's simply the derivatives, to distinguish it from the more usually used rho dot over dot. You know that rho over dot is the actually derivation in time, and to distinguish it from the radial derivatives, we put here just prime, and this prime will further mean that this is derivatives. And also in the same fashion we determine adiabatic temperature gradient in R. This is the only distance we have. So, and it's equal, it's more convenient to determine, because actually for density we should take into account the first derivatives, but for the velocity for the derivative from the adiabatic value, we should take actually, because of this form, we should take the second derivative. So the free constant here, another free constant, this is constant. This is sort of the free constant which drives the convection. And the similar free constant here is slightly different. It's rely on the second derivatives on R. And this is more convenient form in the true way to estimate the derivatives of the temperature. And in the slightly another way, we can estimate the gradient of gravitational potential, which is just directly can be represented via the vector of gravity vector under the area where it's walk. So here it's index O, not 0, but O, which denotes the situation. And also it has a component directly in the spherical radius. So we put it here. And this is just to relate them, that this R component, when R is equal RO, we have exactly the gravity acceleration, which is of course down. Not up, but down, because mass usually gravity acceleration. And here the positive constant rho prime characterizes the radial stratification of the density. And tip double prime also free constant, which we fit to particular planets, to our Earth or whatever we have. This constant characterizes the radial non-uniformity of the adiabatic gradient. Both of these quantities are determined by the linearly varying with the spherical radius gravitational acceleration gradient u minus gradient u originally. So, but here there is another sign because we put it here. And so, of the liquid spherical layer in the deep interiors on planet and their satellite. So the general stationary solution of all these equations, which are listed here, so it's have a general stationary solution, which depend only on R. And actually, we can even write down the equation which we solve, but we didn't solve them, but show what is the equation. Let's start. So first equation is for A. I will see it here. You see that this equation for A, of course, the most important equation, it's Navier-Stokes equation. And it starts from the velocity, but there are different contributions of the velocity. And this velocity, of course, because we suppose that the velocity is 0, we're looking for the solution, for the hydrostatic solution. So this all velocity are cancelled out, but what remains? We just write from formula for A, we have the consequences under the condition that V is not. Then we have that all the velocity cancelled, and then we just could rearrange it in the form entropy alpha T adiabatic over the Cp grad UA. This is one term. And another term, of course, pressure, modified pressure, of course. I just place it in another part of the equation to make it symmetrical. So eventually this works like that. Gradient of the original pressure, or more precisely deviation from adiabatic state, and deviate by rho adiabatic. And also there is a deviation from the adiabatic state for the potential. So we have this equation where when we use in V equal naught. Then the next equation is for cell. Just look. For 7 equation. This equation for 7 again under the condition that it's constant and independent on where the condition that from 4 7. Okay, we start from A, 4 7 8 under the condition that velocity is not, and there is no dependence on the time. I just wrote it like that. So it's easy to see that all these things are completely remove the substantial derivatives, and only things we are left from this equation is that, okay, instead of substantial derivative we have not. Just stress it that it's not not O, and it's equal to this term from S plus Q A rho A T A. So this is the second equation. Then we proceed further. Equation for 7 there are two equations, but the second equation quite trivial because we have velocity equal naught. So actually we have not equal naught, so nothing to write down. Okay, so and then there is 4.6 A to D, 4.6 A to D. And this is just boundary condition. I will not write down them all these boundary conditions because you rather well know. And from this boundary condition, we use only two conditions in this equation. This is condition of the input and output flow, and it's quite important. For another boundary condition, we don't use them because we just suppose that velocity is equal naught, and also there is actually no need to use the boundary condition here because here the solution is quite simple. And finally, we will have, okay, sorry. So this general solution of V equal naught, solution of those equations which are listed here, can now be easily obtained. From it, we immediately isolate the further required sources of convective instability S prime and the time derivative of the adiabatic entropy as we clarified in the formula for 3b. So which is actually integral condition, additional integral condition just to help us to utilize this equation. So I will not show you the intermediate step, how we solve this system. It's relatively simple, but you can repeat this as your exercises. I just will write down the result. And the result is as following. Okay, maybe. Here it's listed on the blackboard, but here perhaps I will. Okay, will it fit there? Hopefully. Okay, maybe I'll write down because it will be quite important. I will write down on this blackboard, separate, why not? And so here I will write down everything which is connected and which is the sort of the final things which we are looking for. So the main source of the convection stability, we mark him as like this S prime, small s prime, and it has an index 0. And this can be represented via the input heat flux minus output heat flux, which is given, of course. Then it has the adiabatic heat flux contribution, which work here on all the sphere. Again, RO. Then there is a difference. Actually, there is a volume of the spherical shell. Here we have a volume of the spherical shell. Cube here. And it's multiplied it by K T double prime, which is given. So this is the adiabatic part, and this is the given contribution. And then it's divided by, it just normalizes it actually, by this adiabatic flux with addition of the temperature for P, T, R, small k, and here we have again the similar adiabatic heat flux contribution. So there is one source. This is all constant are here. So this look like the radial distance. So this is the first. Actually, all these R dependence are coming from this Laplacian equation. The first solution of the Laplacian equation is dependence on R, and another solution of this Laplacian equation, maybe more precisely to say that it's Poisson equation, because there is constant here. So, and the second one is inverse power of spherical radius. So, and it's writing down like this: QE R cube. QO, sorry. Okay, we start here from QO R cube. Oh no, I wrote correctly, but sorry for my mistake. QI RO. Then we minus QO RI. There is some exchange between these two values. Cube. Then we have the similar denominator like this, but slightly different. It's 4p T rho K RO cube minus RI cube. And this is also acting like the, okay, let's write it in slightly different way than in that notation. Inverse R squared. So this is the major source of convective instability. Actually, it appears in the equation later. I will show you in comments. And there is also another source of convective instability. This is direct source of the buoyancy, which is due to the input and output heat flux. And there is some subtraction from this input and output heat flux, which actually there is adiabatic heat flux. So this is the major contribution, which is coming out due to some input or output heat flux. And it's also some advantage of this term is that we can not only thermal convection imitate with this stuff, but compositional convection also could be imitated by this stuff. Because if we suppose that this inner heat flux is positive and has some sufficient value, then it can imitate the compositional convection. While this output heat flux are basically imitate the thermal convection contribution, And this thermal convection contribution could be even in opposed to the generation. But the one which is from the inner core and basically mainly due to the gravitational differentiation, it always has a positive contribution. And the similar play is for this another term, but maybe slightly different arrangement. And the second, also maybe not so also important contribution to the convective stability is actually connected with the time derivatives of the total entropy. This is related to the time derivative of the total entropy, and it depends on the total heat flux, normalized heat flux, which is not this heat flux, but the similar heat flux, which is actually responsible for the radioactive cooling, for example. And it works like that. It has two terms. One is depend on the radioactive cooling, and other is also connected with this input and output heat flux. And it basically, this stuff is working like the cooling down of the planet. Just cooling down of the planet due to the excess of the output heat flux. And here we have the similar denominator for P, T rho, Rho cubed in minus Ri cubed. Okay. So it constitutes the formula which one here 412 and 413. Okay. So here we have some index O that denotes the stationary solution for the superadiabatic entropy. This index O, this one. And the prime denotes the direct derivative with respect to the spherical radius. We have some prime, maybe not so much of them. Here there is a prime. It denotes this value. Actually, it's enough. So, it is obvious that the spherical layers with a negative source of convective instability S, when S prime is less than It is obvious that spherical layer with a negative source of convective instability SO prime less than 0. SO prime less than 0 promotes the development of the convection. So if S prime is smaller than 0, then it's promote convection. This one things. And in opposite case, if it's positive, of course it's acting against convection. And sometimes it happens, especially if this output heat flux is not so sufficiently large. Then, on the contrary, in the layers with a positive source, stabilizing occur. For example, it could be referenced on my paper. We especially emphasize that the convective source 412 does not include the internal heat source Q, which is estimated very inaccurately. This significantly simplifies the study of thermal convection in the deep interior of the planets and moons, since it's reduced it to manipulating more confidently estimated heat flow. No, here there is a reference on Braginsky, Robert, Starchenko, and John's work. we use the simplification introduced at the beginning of this section and the obtained source of the convective instability to finally formulate the system of equation and boundary condition for nearly adiabatic convection in the form most convenient for further use. We transform the equation of motion 4.48, the law of conservation of mass for 0.7b, and the law of conservation of energy 4.78 to homogeneous. So actually without direct sources, it's important that we finally have homogeneous equation in form. So let's write down the final equation. Here there is the equation for the source. Now let's write down the final equation itself. Okay, it's enough space here. Of course, first coming is Navier-Stokes equation. Not so much changes in it. Let's just put in one place everything what depends on V. Oh, okay. Sorry. I should. So then we are writing down the Coriolis too. This is based on the unit vector in the direction of the axis of rotation. And here there is vector product on V. Then there is modified pressure. And then we have contribution of the viscosity. And it's here there is a place where some change things are changed. We have here, instead of the coefficient which link it to the divergency condition, because we have not exactly divergency condition, we have the condition not divergency of V, but we have the condition divergency of rho times V. This is adiabatic. So this term which is related to the divergency in this form, slightly transform it, and it takes the form 3 theta rho prime, which is given above, and rho squared, and gradient of the radial component of the velocity. So this is perhaps maybe I paid too much attention to it. Of course, in the Earth it's not so important, but it can be very important, for example, in such a planet like Uranus, Neptune, and especially Saturn and Jupiter. So, and the next term is not changed, it's just ordinary ordinary viscosity term. And of course, there is a buoyancy term which drives the buoyancy. Go divided by Cp per O. And here we introduce, instead of the deviation from the convective velocity for the entropy, we have anything that is on top of that. You know that previously so actually our deviation from the adiabatic state has two components. One SO and other component, this theta. So we use this relation. Oh, sorry. We just use this theta, which is on top of the hydrostatic solution, which we previously obtained from this system. So it's on top, and this set like that. Okay, let's just stress it. And then there is a divergency condition. This divergency condition is taking into account divergency of the density. So divergency condition is not divergency condition complete, but also it includes dependence on the density. And it takes the form rho strich prime over rho and radial component. Of course, it's again have not so big contribution in the terrestrial planets, but it could be quite sufficient, and maybe even the major contribution in such a planet like the Jupiter and Saturn. And then we have perhaps the most important equation in all this system. This is the equation for the entropy, but not all entropy, but this entropy which is on top of the hydrostatic solution. And this is actually, it could be written like that, d theta by dt, very substantial derivatives. Then we have the ordinary term like k q theta. And the main things here which is appear and which is drive actually the convection and include all the input, output, and so on flow is namely this term which we specify here, and it's multiplied by the radial component of the velocity. So perhaps it's the main drive. I just stress it out. So eventually we have 414, and there is A, B, and C. I just substitute them via the comma. From here on, the effective pressure per unit of density from 4.48, number it. Perhaps the most important and difficult equation to solve in the original system of planetary convection system is Navier-Stokes equation of motion. So you can see this equation in the various publications, including our consideration. So I will not repeat its general form. I just repeated form for this Busse approximation, which of course some simplification, but rather sufficient to our first goal. And here we can write the third equation, which is Navier-Stokes equation. In this case, it looks like, okay, I should move. Okay, I just show you equation. And here perhaps also important thing happens, that to write down this equation like it was written here, it's necessary to suppose the following condition for the thermal expansion coefficient. And then we have this second equation, third equation, sorry. Equation which is in fact Navier-Stokes equation. There is a Coriolis term, of course. There is the unit vector in the direction of rotation, and it's multiplied by the cross vector product on the, oh, sorry, what I love. I wrote the magnetic field. Sorry. Of course, velocity. Okay. And then there is such a term like a grad P, capital P. It's important to know that it's capital P on rho. Rho we regard as a constant. This is the density. And also we neglect all the component of velocity which are not working in this approximation. We leave only Laplacian one. This is kinematic viscosity nu, and there is Laplacian of V. Okay, and the remaining term is the gravity potential. So it's 5.3. Okay, here we consider fluid of uniform constant viscosity nu, which rotate with the constant rapid planetary angular velocity omega about the constant unit vector 1z, fixed in space. Then centrifugal acceleration in 5.3, in this formula 5.3. Oh, let me proceed. Oh. Okay. 5.3. The centrifugal acceleration in 5.3. I always have the message with glasses. Oh, sorry. Okay, the centrifugal acceleration in 5.3 is neglected with the accuracy of order 0.5%. So we just even don't write it down, but it in the comparison to the standard gravity acceleration. So we use the standard gravity acceleration, which is actually this grad U. So in other words, this is gravity acceleration, which usually denote as G. Gravity. And it's much more than centrifugal. So we neglect centrifugal. Okay. And the final Newton self-gravity planetary equation is actually nabla square U is equal 4p gravitational constant and rho. Of course, it's the same equation which we consider with U, but only in some simplified form. And the temperature profile in our spherical geometry can be presented in the form. We present the spherical profile like steady temperature profile. Okay. There is a steady part which depends only on radius. And there is unsteady part which we denote here like tau. And it actually depends on all coordinates. Let's put all coordinates like the r vector. And of course it depends on time. So it's actually the value we are looking for and examine. And here tau s is the steady temperature profile, and tau which depends on all coordinates and time. This not depend only on the radial coordinate. Steady temperature and ice. Actually, this tau is convective part, which is called the convection and support convection and so on. So, to be consistent with previous studies of the linear stability of thermal convection in a rotating and spherical shell, for example, there are many references there. We take the outer radius of the layer RO as unit of length. So here in this approximation, we will follow the initial contribution which was made for this person, and they usually used even not spherical shell. They started with using the complete sphere. So in this condition, it's not convenient to use the radius of the inner core, but it's more convenient to use the radius of the outer core. And in some cases, even the radius of the sphere. If we consider the sphere, of course, the first case which all people consider is just sphere. We fill it completely by the liquid, and there is a constant heating inside it, like the radiation of heating and so on. So we take the outer radius of the layer as the unit of length, then the viscosity. So unit of length, as we discussed that it's not good to make R, let it be L. Units. It's of course the radius with markers but star units of length from the both length. So it's the units of length. It's the ratio of the sphere. We will not specify outer sphere, any sphere, at least some sphere which is on top. Okay. So then we use the viscous time. Viscous time is quite naturally appear as a typical time. So typical time T with star is equal. If you consider the dimension of the viscosity, you see that it's actually meter square per second. So to construct from this value the characteristic time, it is working like using again characteristic length. So it will be RO squared over the viscosity. So we use this like the characteristic time. And the effective pressure, quite useful in this respect to measure. So we have the effective pressure value. I just remind you that the effective pressure is not just pressure, but the pressure divided by the density. This density is constant here, and it simply scale it out of the system. So the pressure will have the natural units of 2 omega nu. We use this representation because the pressure, first of all, compensates Coriolis force, this Coriolis force. So we use it as a unit. And then, using these units of measurement together with the above parameter, we obtain in dimensionless linearized system of Busse equation. Okay, will it fit here? Okay, I'll try to fit it here, but I'm not sure that I will fit. Okay, let's try. Okay, first equation is maybe there is here. Okay, there is a non-dimensional equation. Let's write them down and comment. First one is, of course, divergency free condition. And we number it 5.48. Then the next in importance is the Navier-Stokes equation itself. So, and it has very interesting form. There is Ekman number, which you know, I will not define it here. You know the Ekman number, so I just wrote it in right place. And there is a substantial derivatives of the velocity. There is, of course, Coriolis term. And because we scale it out omega from this equation, so it has a rather simple form. And of course, there is a pressure, again modified pressure, actually pressure divided by the density. And all that is equal, again, Ekman number. Then Rayleigh number appear. I will describe it later. And in front of the Rayleigh number, we have this tau, which drives the convection. And there is simply vector of the radial spherical vector. And the final term, but perhaps the most important one, because it's actually produced the influence of the boundary condition of the flow, is the viscosity term, which in this non-dimensional units becomes like that. Pi 4b. Okay, you see that even at the first glance, you see that you give rid actually of this term. And this is a very good thing, but nevertheless, it's, you should be a bit careful because sometimes there is some derivatives here. And there is some time where we cannot completely neglect that stuff. We should take into consideration some short times and some derivatives which appear here, especially we consider it. But at the, if you like, zero or maybe first approximation, we can just disregard this term. If we disregard this as well, then we have a geostrophic flow, actually, type of the geostrophic flow, which could be also estimated. But to solve the problem completely, we should keep that. First of all, of course, to keep all the terms, except maybe this one. Because especially in this, its nonlinear part, it's not so important. Okay, so let's proceed the final equation. So the third equation in this system is the temperature equation. It includes Prandtl number. Then it includes this instability contribution, which is very similar to the contribution we discussed previously. So this is instability contribution, which is due to the gradient of the imposed temperature. So we have usual condition to model this value, this thing is to have one temperature on one boundary, another temperature on another boundary. So there is a gradient of temperature. And it has some hydrostatic part. And this hydrostatic part is actually the main driver of the convection, which manifests the convection instability. And this gradient T is simply multiplied on V. And since this gradient, as already showed you in my previous presentation, is basically on R, so all this combination finally means that here we have derivatives and here we have just R component, because this depends only on R. Let's just split. just to understand that actually, namely radial component of the velocity produce the convection here. So, and also, of course, there is the diffusion term, which has very simple representation here. It's just nabla square on tau, or as was lambda tau. Okay, let's A, B, C, 5, 4, 3. Okay, let's just, okay, I will not write down the Ekman number, you know it very well. The only difference in this Ekman number and the one we used before, maybe you see that there is no 2 here. So actually we use this 2 in the Ekman number, in determining the Ekman number. So maybe it's worth to write down this everything. First of all, we write down Prandtl number. Prandtl number is, okay, are they listed here? Not. Yeah, everything is listed. Prandtl number is ratio of viscosity to diffusivity. Then Rayleigh number is the ratio of all the terms those are responsible for generation. This is alpha expansion coefficient. So it's show how much is the expansion with the change of the temperature. If temperature rise, so in corresponding relation, this alpha coefficient gives. Okay, maybe I was a bit in a hurry. So the next Rayleigh number, which is equal alpha Ts prime, actually derivatives of this state. Then there is gravitational acceleration on the outer boundary, and there is the radius of the outer boundary. So actually all this stuff is quite sensitive to the size, because you see that here it's entering 5 power. So this is the reason why this Rayleigh number sometimes could be very big. For example, on the sun it could go up to 10 to 30. And the Earth it will go up to 10 to 20, 25 or something like that. So, and on the bottom we have all the effects which are against generation of convection. So this is in favor of the convection. And also there is one thing, that this gradient, actually there is a prime mean derivatives, it's negative, as we already told you. So just to have the positive value, we put here minus as well. And here on the bottom we have all the terms which work against the convection. It's of course viscosity and diffusivity. And the Ekman number here, which appear here, is slightly different, and this difference is quite obvious. We just include 2 in this. Not we, but Robert and Busse. Okay, so they started this stuff. Two is here. Okay. So I just remind you that the alpha here is the coefficient of thermal expansion. Mu is the kinematic viscosity, K is the thermal diffusivity, and G naught is the gravitational acceleration, and exactly at the outer boundary or the radius of the outer sphere. When the fluid is at rest, the steady temperature profile Ts of air from air, and its derivatives depend on the heating mode that is constructed. Most of the known works consider either so-called internal heating or differential heating. In the first case, it is assumed that the distribution of the heat sources is uniform in the fluid volume. In the second, that the temperature values are fixed at the inner and outer boundaries of the spherical layer. And let's follow the work of Domi and others, and we write this profile in this form. Actually, this profile determines all the, okay, I started perhaps from this point to state the system. And to complete the statement of the system, we should show the profile, this TS profile, which actually drives the convection. And in case of the internal heating, this profile works like that. Ts is equal minus 1/2 beta r square plus TO. TO is the value on the boundary, value of the temperature on the boundary. And actually for us not TS is important, but important is the gradient. And the gradient actually is equal, because gradient is entered here. This gradient is equal, as you easily could see, minus okay, I remove that number because you know it, so I remove it just to give a space for that. So it's equal beta r and the unit vector in the radial direction. It's constitute formula 5A. So this is the internal heating, and also we could have the differential heating. This actually works when we have some value which is distributed uniformly of the heat flux inside the sphere or spherical shell or whatever. But it's possible to have the differential heating when we have one temperature on one boundary and another temperature on another boundary. In this case, there is a slightly different. So differential, and of course again heating, the same Ts, the similar Ts is T1 over R plus T2, and the gradient is again negative, minus T1 R squared R. Oh no, not R. Unit vector in R direction. This is differential heating. Okay, I succeed to fit everything. And here TO, T1, and T2 are the constant determined by the boundary condition. Actually, it's not exactly the temperature corresponding, but it's some constant which we can find in the within the boundary condition. So okay, since I spoke even slightly more than 1 hour, so we can finish this part. And of course, I'm waiting for your questions. Okay, please.
It has TS prime.
Hmm?
So TS prime is basically the differential coefficient of TS with respect to R.
No, TS is the given profile of the temperature field. It's just given profile of the temperature field. And this profile is usually if we have internal heat sources which are distributed with uniformly distributed in the spherical shell. So it has this temperature profile is look like that. So its gradient is actually just proportional to the R. But in the case when we have differential heating, because as you are asking, we put one boundary at one temperature and another at another temperature. Usually, for the case for the Earth, we have inner boundaries at higher temperature and outer boundary at lower temperature. So the effect is that it's heated from below, and is correspondingly it's cooling down from above to support to maintain the fixed temperature. And this is so-called differential heating. And this differential heating works like that. The profile is in inverse R plus some constant, and the gradient is just inverse R square.
So what is TS prime? TS prime in the Rayleigh number
TS
equation?
prime is the gradient. This gradient. So TS is dependent. TS without prime is dependent on radius.
Okay.
And the prime means that just derivatives in the radius.
So it's basically the gradient evaluated at what point of R?
It's some average.
R not. I mean R's a typical value.
Because when we determine this Rayleigh number, usually we speak about some average values.
Okay. Thank you.
Okay, one more question. Actually, negative signs means that the temperature is rising with the depth. So in case of the Earth, the more deeper we are, the higher the temperature. So it's in inverse order that if air rise, then this gradient will be positive for air. But in contradiction, the temperature is declining with the growing of radius. You grow radius, and growing with radius, the temperature is declining. So it's actually resulting in that minus in the gradient. So we just of course we could consider with this prime some, I don't know, average or modulate stuff, but we just using sort of the original approach, so they use it like that, so we just follow. Okay, yeah, exactly. Yes. Thank you. To make this things a bit clear. Thank you. Okay. It seems we spent more than 1 hour, so perhaps we have to have some small break. Or maybe big, I don't know what Rani said. Maybe just small. Maybe just small to finish up.
Small break.
Yeah, small break. This effective pressure. This effective pressure is now denoted by the letter P. We just to understand that this is actually effective pressure, but because it's only entering in one place, why not to have some extra addition to it? We just replace it by this P value for simplicity. So not to be confused with the, it's preferably to know that this pressure not to be confused with superabatic pressure from the previous section 2 and 3. And the specific entropy, other words, we can reformulate this, that this specific entropy theta is equal as O minus S. It is the same stuff. Here and below represent not the entire, see above, terabatic entropy, but its dynamical path minus the stationary solution, which is necessary, is obtained from 4.12 and 4.3b. This one. This 3b, 4.12 is here. Okay. The chosen homogeneous form of the heat transfer equation 4.14, this equation, allow us to write the thermal boundary and normalization condition also in a simple homogeneous form. So actually, after substituting of all this stuff, we simplify somehow the boundary condition for this value, because it's on top of the hydrostatic equilibrium, and simplify the equation. So of course we have the normal boundary condition for the velocity. I will not list them here because everybody knows, but we should specify the boundary condition for the entropy. So finally we have d theta. More precisely, of course, not entropy, but the entropy path which is on top of this hydrostatic path and on top of adiabatic as well. So it's just some additional stuff, and it's d theta by dr. Actually, we can put it in 1 at r equal ri and at r equal ro. All of them are equal not. So there is two conditions here. And there is one integral condition which slightly changes here, because it takes form of the integral over all in a sphere, over all rotating liquid sphere. No, sorry, liquid spherical shell. Yeah, of course, liquid spherical shell. Ri and Ro, and this integral is acting on 1 minus rho prime, which is constant in our condition, over rho also constant in our condition, and here we have r. You can see that the dimensions are satisfied. So then, and it's this integrate over the theta, over theta on the volume. So this is boundary condition constitute formula for 15 A, B, C, 3 formula. And more precisely, this is not boundary condition, but integral condition, global condition is possible to say. And these two boundary conditions, just homogeneous and simple conditions. And we need that because we put this condition on derivative, so we have it's necessary to have extra condition to determine the complex function. The final almost adiabatic system of convection equation, which is written on this blackboard completely, is closed by the boundary condition on velocity, which I, as already told, is quite obvious. I will not write down them. And for example, for terrestrial planet, it can be written in the form of no slip condition. This is no slip condition means that it's all the other what it means that directly on the boundary we have zero velocity in the system of coordinates which are taken together with this boundary. So this is other representation of no slip condition. Okay. It seems I finished this part. So maybe there is some question. Yeah, please. 2.12, yeah. S null must be greater. No, to promote the convection, it should be less than 0. Yeah, to promote the convection, it should be less than 0. So here, if it's greater than 0, then it's suppressed convection. So making some things more stable.
Sir, 4.14b, that 4.14b, the continuity equation.
One, yeah?
Can you comment on that once?
This 414b originally it looked like that. We have this is equal naught. If we expand this row,
yes,
over the constant term and the term which variate so we have gradient of rho, say rho O component plus rho prime R. This is also constant, rho prime, and this is constant, it's some average. Then, okay, better here. Another bracket. If we open all the brackets and act operator number only by R,
okay,
because only R is acting here, so we get this.
Okay, okay.
This one.
Okay, sir.
Okay, one more question.
Sir, previously in the basic equation of planetary convection, we neglected that term, that zeta. In the gradient of in the momentum equation, right hand side first term. So in the slide only. No. Previous equation 4.14. Yeah, we were neglected the right hand side of first term in the basic equations of planetary convection. No, sir, the first equation.
First, now yes.
Yeah, Navier-Stokes equation.
Yeah, what you want to neglect?
Yeah, previously we have neglected. You have told us that the divergence of del dot V equal to 0. But here we have taken the divergence of del dot V equal to that constant of...
Which divergence? I don't know.
Yeah, that's right.
Please
Okay.
Please say this divergence.
Yeah.
You speak on about this term. Okay, this is
okay. But
actually in our previous consideration we neglect this term in But here I return this term just because I am trying to write down more general equation than we previously considered. So the maximally possible general equation. So now actually, when we return this term, you should consider not only terrestrial planets, but also the planets like Jupiter, Saturn, and for example, icy giants like the Neptune. And so it's just and it's not required too much effort to include this term. So actually, it's just the thing which, but of course, in terrestrial planet this is small, because here the variation of the density is just 10%. So it's normally at least 10 times lower than this one. But in fact, even more, because effectively we have here just gradient of the arc, and here we have double derivatives. So if we divide it on the small value, then we even raise the ratio. Of course, in terrestrial planet, but in the such a planet like a Jupiter, where density change more dramatically, this term is working. Something like that.
So especially for Jupiter, Neptune, and Uranus, these
exactly,
kind of terrestrial planets only we will consider.
Exactly.
Okay. Thank you.
Okay, let's have a break. Or maybe somebody will ask more. Okay.